Okay, good morning. This is Larry Olson with Olson Engineering and Instruments, located in Wheat Ridge, Colorado, which is Denver. And it's my pleasure to welcome you to our webinar. It'll run from 9 o'clock Mountain Time to 10:30. We're generally keeping people muted, but if you have a question and want to ask it, feel free to unmute and ask your question or put it in the chat, and we'll check the chat for questions. There will be a little bit of time at the end of my presentation, which will be on non-destructive evaluation, load testing and monitoring of bridges. And we also have a branch office in Rockville, Maryland. And then Dr. Guido Kamada is also a professor. He's the technical director of ASDIA USA. Will be speaking on experimental and advanced numerical simulation for digital bridge twins. He does have a Colorado connection. He got his PhD and was a professor. Oh, okay, I have to mute my phone. Okay. Sorry about that. Meant to do that. So, as I was saying, he got his PhD in structural bridge engineering at the University of Colorado at Boulder, and also was professor there, as well as being a professor in Italy, where his main company, ASDI, is located. He'll tell you more about his background, but he'll be speaking in the second half of the presentation on experimental and advanced numerical simulation for digital bridge twins. So with that, I will get right into the presentation. Just a little bit on my biography. I don't need to dwell on this too much, but naturally been in a variety of societies, certified in National Highway Institute certification for bridges on safety inspection, fracture critical bridges, load resistance factor rating, and ancillary structures. Active in American Concrete Institute for many years, became a fellow. As president of the national chapter of ACI when we got our office going back in the Metro Washington, D.C. area. And then on 228, non-destructive testing, consolidation, and bridge evaluation. Also very active in the International Concrete Repair Institute. Became a fellow, founding chair of the evaluation committee, and been on the board in the past. Teach ASCE public and private seminars on condition assessment, existing structures, bridges, and dams. On past committees on Transportation Research Board, which has been extensively reorganized on tunneling, earth exploration, and field testing of structures. Involved in the United States Society of Dams and registered PE in many states. Back in the day, I got my bachelor's and master's in civil and geotechnical from the University of Texas at Austin. I was lucky enough to become a distinguished alumni in 2006, and I spent my first 5 years working as a project geotechnical pavement and materials engineer in Denver, Colorado for CTL Thompson. So the corporate history, I started the company in 1985 and focused on imaging infrastructure for assessment, monitoring, repair with non-destructive evaluation and geophysics. And Olson Instruments started in 1993 as we wanted to have instruments for our own use and then decided to sell them for testing concrete, asphalt, masonry, and wood materials of structures, pavements, foundations, and seismic soil and rock properties. That is our office shown there in the west side of Denver, close to Golden in Wheat Ridge, Colorado. If you're ever in the area, feel free to reach out to us and come visit. Be happy to do so, as well as back in our Rockville, Maryland branch office. So the services we provide is broad for assessment of bridges, pavements, foundations, tunnels, buildings, and imaging subsurface conditions. A lot of condition assessment for structural integrity. It could be aging infrastructure, older bridges, dams, buildings, etc., with problems, or it could be new construction with problems such as void, honeycomb, cracking, things like that. We do geophysics for engineering, environmental, and groundwater projects. Bridge and building load tests, we'll be talking about that today. Structural health monitoring is part of that. And Dr. Kamada, Guido was speaking very much on that, why we are looking to work together and pursue projects together, as we'll discuss. We also do vibration monitoring, applied research and development, and training seminars, as are listed there for ASCE and our own annual seminar as well. So we work nationally and internationally. So the first thing we're going to talk about, which was mentioned in the announcement of the seminar, is sonic surface scanner for looking at delamination, the integrity of bridge decks, the thickness, could even be void, honeycomb, and cracking, but commonly it's older bridge decks and looking for corrosion-induced delaminations. So we got a research contract on impact echo scanning for bare concrete. It was under a National Cooperative High Research Program Innovations Deserving Exploratory Analysis grant. And This is the end result of a cart with rolling impactors, sensor wheels, with solenoid impactors and displacement transducers, two wheels on each side, offset if you're doing impact echo. Surface waves can also be done when you line up the wheels to go through asphalt overlay decks to define top and bottom delaminations. And in general, it also has applications on asphalt pavements, but looking at concrete and asphalt quality, the cracking damage, the pavement thickness is elastic modulus for strength estimation, which is most accurate when correlated and calibrated with cores. So this is a close-up of those sensor wheels. We slowly walk at about a mile an hour. And as it comes around and this weight of the wheel pushes onto the rough concrete deck or pavement or asphalt, the solenoid comes down, hits it, and picks up the response with this displacement transducer that's protected by a thin urethane tire. So the INDOT, Indiana DOT, worked with Purdue University and sponsored this long-term project and network level NDT implementation plan for Indiana. The report is listed there with a link, and they evaluated a whole range of NDT consultants and methodologies, ground penetrating radar, air launched and ground coupled automated sounding, acoustic sounding with chain drags and automated sounders by various people, impact echo, our scanning system. Indiana DOT owns 3 of these systems now and have tested approaching 1,000 decks across the state on bare concrete. Infrared thermography, it was found by the research to be the most accurate scanning method for delamination mapping with correlation 100% with cores that was predicted. And they compared both our scanning work and the Indiana DOT group led by Prince Ba with INDOT, their scanning work on bridges, and it agreed very well. That's all in the report. This was independently done with Purdue University serving as the independent research agency and various agencies as well as Indiana DOT did the testing. So that's out there and available. So I'm going to talk about what was found. The impact echo results compared well between ourselves and the Indiana DOT. Cores universally confirmed the results. The infrared thermography was comparable between the entities, but affected by shaded deck areas, moisture, and small temperature differences. And it was still fairly accurate, particularly when they used a thermal stare approach that sits there for over a day. And the ground penetrating radar was very good, of course, at detecting the rebar cover depth, but the bridge deck deterioration results had a lot of variation in values and locations between the different groups. So they didn't think it was the sole method, but it was valuable for corrosion activity and kind of a network level mapping because of the speed of automated radar and driving it. Automated sounding was not so accurate, maybe because Indiana tends to have latex modified polymer overlays that could make the depth of the top rebar steel greater than you could easily audibly hear, which in our own experience is around 3 inches. It's hard to hear anything deeper than that from a top hollow sounding delamination from chain drags or sounding. So some recommendations, they recommended aerial infrared thermography as a network level inspection. Impact echo was recommended as a project level test for the future assessment to detect delamination discontinuities in bridge decks where you have to have traffic control. And the pole mounted infrared thermography, they like that as a secondary project level test. There's also similar aerial infrared thermography from flying drones off to the sides that can be done repeatedly, like hourly, and averaging out the results in a simple sense to get a better interpretation. So these were the bridges that were done, scattered around the state. There's Indianapolis. Talk about one of these bridges in particular. There you can see the INDOT technician pushing the system along, and one of our people was pushing it along there. And the traffic control, you can see the cones and everything is necessary. And this shows we also did ground penetrating radar, the TSSI system, 1600 megahertz. Both had GPS on our unit for very accurate mapping within a few centimeters of locations. And on the bridge deck, basic impact echo is the depth equals a factor, which is about 0.96 for a slab or wall, times the compression wave velocity, speed of sound divided by twice the frequency of the resonance. And this is a resonant echo, meaning the sound wave is echoing and resonating back and forth top to bottom. So when you have a single thickness echo, that's great. It means it's a sound deck. You could have a situation where you had a tight crack where you still get some energy through it, and you see both the higher frequency, shallower crack echo, as well as the bottom of a deck echo. Deeper cracks, lower frequency of echo, and top delaminations within the first 3 inches end up showing up as a flexural resonance, which makes that hollow drummy sound. Very low frequency, it looks much thicker than it is. But when it's within 3 inches or less, this horizontal delamination crack associated with the top rebar, you get this very high amplitude, audible flexural resonance, not an echo resonance that looks thick. So this shows one of the results for a scan of a single wheel. This is 0 to 120 feet. You're looking at nominally a 9-inch thick echo. Where it shifts to the right up towards 20 inches, these are delamination points. These are the thicker ones. And so this just shows a typical sound result. You can see the time voltage signal there. This is frequency from 0 to 50,000 hertz. Very clean 8.8-inch echo for that speed of sound. And if you can calibrate based on a known thickness or doing surface waves, you'll get a more accurate thickness echo depth. But in any case, that was right on the money for this project. The results on a discrete point-by-point basis are showing on an echo depth scale in inches, where the delaminations are really severe ones, are 14 to 20 inches thick. That's thicker than the deck was. That's that false flexural resonance. And then some minor delaminations, the gray scale being on this deck, the nominal 8 to 11-inch range of the thickness of this deck. And then shallower delaminations down in the darker blues, 3 to 5-inch depths are shown as well. So this is a little hard to look at. So what you normally do is it's plotted with Golden Surfer software, and it basically contours it. So now it's a little easier to look at. You can see the top delaminations, the deeper bottom delaminations also stand out. If you have a severe delamination, you won't see through with impact echo to the bottom delamination. But where it's not, and it's out from under, if you will, a top delamination, you can find the bottom delaminations as well. So this just is, we did a simple photogrammetry approach with orthomosaic analysis of this. And you can see that just by walking around with an iPhone, you'd normally in a larger deck mount it on a vehicle with a camera, but we were able to stitch together a good image of the deck. And we overlaid the results on that just to compare them in plotting. We also did the radar. This is one of the radar scans. It shows how the steel is varying between, say, nominally 3 to a little over 4 inches deep in this particular location, along a distance from 0 to 75 feet. So in radar can also be analyzed, and the principle is that you're looking at attenuation for corrosion. But this is showing the depth of cover range quite a bit, from as low as less than 1.5 inches up to as deep over 5 inches. So this is a good cover map. Tying that in with chlorides, depth of carbonation, predicting remaining service life is important to compare that with the damage maps as well from delamination surveys. When you analyze radar data, which we do, you get attenuation. And what you're looking at is, this is the 20th percentile amplitude of data, indicating because of the corrosion byproducts, the signal is more attenuated. That's a likely indicator of corrosion. Unfortunately, as shown in research and other things, it could also be due to moisture, presence of de-icing salts. Other things can affect it besides just corrosion of rebar. So GPR is excellent at finding depth of rebar and mapping it. Can be done 2D and 3D as we've done, but it's not as accurate, and that's what the Purdue study showed, for determining the extent of delaminations. So that's just showing the amplitude in decibels, and the yellows are showing likely corrosion areas. So when comparing the two results, you can see there's some correlation for sure between the impact echo scanning with its highly accurate results of mapping top delaminations. And keep in mind, radar is not going to find deeper corrosion. It can find deeper steel, but it's not going to be able to analyze it for corrosion because of the interaction with the top steel. But it's showing some correlation, but it's not as accurate when you compare it, and missing some things that are showing up in the impact echo. And very detailed summary tables were provided for each of the bridges in terms of sound conditions, near surface delaminations, the amount of percentage of areas and areas as well, both uh, deep top delaminations, bottom delaminations, a variety of things were reported. This is a project, I'm showing it briefly, when decks get really long, or in this case, a concrete pavement that had similar problems at the dowel joints of a horizontal crack like a delamination, but is associated with curling and warping of the interstate pavement. And right around the joints, there were a lot of cracking damage because of the warping and the restraint of the dowels. So we put 2 sets of wheels, 4 total wheels, behind a truck and slowly drove it and did the testing every 6 inches as it would roll and impact. So here you can see on the wheels, it would hit on the left, it'd roll 3 more inches, hit on the right, then it'd roll 3 more inches, hit on the left. And that was happening on both pairs of wheels and recording it. So what we got in results there is from 0 to 520 feet. Here we're looking at the dowel depths with nominally around 6 inches deep on this nominally 12.5 inch thick pavement, which you can see the main pavement is there. But every so often, right where the dowels joints are, we were seeing cracking damage. And this shows an example result, 12.5 inch thick echo, 6,700 hertz echo frequency from this signal at this cursor location. And here we are showing the reported results of the in red of where at the dowel joints, the yellow shows the dowel joint locations. The outside and middle lanes were the worst on both directions of this 6-lane pavement. We did 42 lane miles of pavement, slowly scanning it during the day when possible, at night when traffic control was an issue, in about 12 field days. So that was a lot of tests every 6 inches to map out the damage. So quickly on asphalt overlay concrete decks, sounding, it really is hard to hear concrete delaminations under asphalt. Infrared thermography similarly has trouble with the asphalt. But scanning often absorbs the energy unless it's colder and more concrete-like, because asphalt velocity varies a lot. When it's cold, it's much faster and more like concrete. And as it gets very hot, it's much slower. So it doesn't resonate as well in our research and testing. And radar can be complicated again by the de-icing salts and moisture that's often at the asphalt concrete interface. But surface waves we found in a study, the Sharp 2 R06D hot mix asphaltic concrete pavement delamination study. We participated in that at Auburn University. It's been reported. And we found there that we could see debonding, this delamination they called it, between the lifts of a constructed asphalt pavement with various debonding conditions and depths at the test track down at Auburn University. So having learned that, we did a project for the Colorado DOT. They gave us access to demonstrate the technology and try it out. This was before we even had a CART early system. But we lined up the wheels so we get one impact echo result and 6 inches apart. And normally the wheels are a foot apart in scanning bridge decks. They can vary from 6 to 24 inches apart. But we got then surface waves between the lined up transducers. Instead of being offset 3 inches to do an impact echo here and hit here, we did one impact echo test, and that same impact generated surface waves between them, 2 transducers. So what do you get? These are the 2 signals. You window in on the big energy because although compression wave energy from impact echo is only 7% of the impact, surface wave energy is 2/3 of the impact. So it's a big spike, and that energy is very strong. And you analyze the difference between this peak and this peak using what's called a phase analysis, where velocity equals frequency times wavelengths. It's the basic physics. And you end up getting this velocity from about, an inch and a half out to over 10 inches of around 5,200 feet per second. So, and this is phase where one cycle would go there. This shows debonded asphalt. Now, this is at 3.5 inches. This is on a concrete overlay deck, that one we were just testing on a regular maintenance and repair project for this state of Colorado. And this shows a delay in phase. Well, that delay in phase results in a drop in velocity at a wavelength that's approximately the thickness of the asphalt at 3.5 inches, going from 5,500 feet per second to 4,500. That's a lack of contact. It's slower. There's still contact by gravity, but it's much slower because it's not bonded. And so it drops velocity. Going deeper now, and the wavelengths on the bottom are from 0 to a foot. Now it's shifting to 5.1 inches, that longer wavelength is approximately depth. That little glitch here is showing a top steel delamination. And this one shows both asphalt debonding at 3.2 inches and a bottom steel delamination where the velocity dropped again at 7.4, these two delays in phase. So we plotted all that up, gave the state this map showing where we predicted delaminations in red and being the most severe. And they scraped off the asphalt, used hydrodemolition to remove the damaged concrete, and showed that, yeah, there was a good correlation between this photograph of what they found from 4 to 8 feet, where we were predicting. You can see where the hydrodemolition has removed the loose spalled concrete, because steel expands up to 6 times in volume as it corrodes, spalls it away. And we were predicting that very accurately. So we've gone on to test many other asphalt decks with it. So now for the last portion of my talk, I'm going to shift to bridge monitoring and load testing. I'll go through this as an introduction to how we can work well with ASDIA and Guido's company on supporting what he'll be talking about in digital twinning with the structural monitoring. So this just shows some work we've done over time on bridge load tests with strain gauges and displacement lasers, and also more recent, also starting around 2010, we started doing bridge load tests, monitoring and stay cable force, resonant force testing with a terrestrial interferometric phase radar system. That's basically by IDS Georadar out of Pisa, Italy. They're now part of the Hexagon company. I think most people know what structural health monitoring is. I'm not going to dwell on that. But it's often done for what I'm going to talk about is more like active load testing and monitoring, not long-term. What Guido will talk about is long-term monitoring. And we have had our own PC. We adapted one, a couple of them to do the field work with 16 to 32 channels. We could take a variety of sensors like strain, potentiometer, LEDs, vibration, thermocouples, etc. Guido will show an integrated fiber optic system that supersedes this for long-term monitoring. This was much more of an active system for testing a specific bridge on a short term, but it can still record the data from strain gauges, etc., potentiometers, thermocouples, vibration, pressure sensors, all tilt meters, all these different things can be recorded. So the data is used so you can understand the loads, the seismic dynamic response of a bridge, early detection of damage and fatigue. This is something Guido will speak to. Designing repairs, retrofits, calibrating finite element models. That's the digital twinning that I think you'll be very interested in what he's going to show there, and helping to monitor both the safety and evaluating the performance of the structure. So this was a steel bridge we did a load test on. The heaviest load test we've ever done is 275-foot long span north of New Orleans, crosses the Mississippi River. This is on the shore, and the river is just over here where the trusses are. And but these steel girders are right here. The one we were testing is this long span. And they had 4 beam trusses every 25 feet. Fairly deep girders, 2 foot wide, 2 inch thick, 10 foot deep. So we mounted strain gauges. We worked with a structural engineer who had done a finite element model. We first did load testing with a 76,000 pound 18-wheeler to prove out his model and see that he would be comfortable with the ultimate load that had to cross it, which was this 18 axle 608,000 pound load test that was being done. And I called it a load test. They had to move this oil and gas vessel across the river for shipping. So you can see that it's a unique vehicle. There you can see the strain gauges mounted. And I'm standing there. Of course, it was such a tall vehicle, it took an extra day and a half to get there. They had to cut down all the power lines along the way. And of course, when it finally got to the bridge, everybody wanted to go to lunch, so it was the only time there was traffic. But it only took about 5 minutes to slowly go across the bridge. But it pops out the axles, it distributes the loads on the bridge, and you could feel it move. So there's our team that was recording the data with the PC right there at the bridge. And we shot a laser down because on the bank, picked up when it was at mid-span, when it was just touching the pier to cross the long span, it was up at the middle 0.7 inches. As it got to the center, it dropped 2.8 inches. And then, of course, it went away all in less than 2 minutes. So you could feel all this movement, and it was an easy way to check it with a physical displacement. We also did concrete bridge load test, where we had our concrete strain gauges mounted on this bridge. They wanted dynamic data, better load rate the bridge, and look at load factor distributions to the girders. We put some gauges right on the rebar as well. These are some of the concrete gauges. Here is the load testing done with the typical 76,000 pound semi-load truck. There's Pat Miller, our now vice president, associate principal engineer, taking the field data, showing the strain gauge responses. I think I skipped showing the strain gauge responses on the previous one. I will mention that it went up to about 1/2 of yield on the large steel bridge. I somehow dropped that slide in this particular presentation, but it was still judged to be safe at 1/2 of yield. But of course, that's putting it quite a ways up there on the performance of the U.S. Steel 1989 girders. So these were taken. We had static, slow, and fast responses on the gauges. So all that came together. This final one we're involved in is a New York City area lift bridge structure built in 1934. Here they wanted to check the bending stresses and rotation as the bridge was opening and closing to see what the stresses were. So we mounted the strain gauges, took the data again, recorded all that. Here's the event A is when the bridge starts to open. Event B, the bridge starts to close. And you can see the strain gauges levels here are given. So all of this data was provided to client to help them answer those questions. So, it's out of order. I thought I had this slide in here. This is the case study for the large overload on the steel bridge. And on the left is the 76,000 pound tractor trailer proof load, if you will, the standard highway type load. And you can see the strain levels are not so much, maybe 40, 50 microstrain, up to 60. And the two axles are showing an effect. But it was up much higher, 350 microstrain on the same gauges during the actual 608,000 pound load test. So we all got up much higher strain levels going through that. So shifting gears, the IBIS system, I mentioned this by IDS Geo Radar in Pisa, Italy. They also have a U.S. office in Golden with Hexagon now. And this is a bridge close to our office, concrete bridge that when it's concrete and not steel, you have to mount reflectors. So we mounted these reflectors on there. The radar, you shine it up in the air, you point it at your bridge, and it precisely measures displacements. We also have the slope monitoring system, which is called an IBIS-L, and that's where you have a rail and it goes back and forth 2 meters to check for slope stability and movements every 5 minutes. You can use that on landslides, dams, and other slopes. But in this case, it's simply mounted on a tripod. You point it at your structure. So these corner reflectors are needed because it's not steel. If it's steel, sometimes you don't need the reflectors. So the basic idea is it's like the INSAR satellite work from space that you hear about of seeing displacements of the Earth, but it's more precise because you're on the surface of the Earth. It's terrestrial. So if you send out a signal, and this is high frequency radar, typically 17.1 to 17.3 gigahertz, which means it's short wavelengths, 0.75 inches. The reflection that comes from the transmitting antenna comes back to the receiving, the change in phase, and it's typically 1/200th of a second sampling rate. In that change in phase, the math tells you it's equal to the wavelength divided by 4 pi times the change in phase between the two signals. So that's the simple calculation that's all done very fast by all the electronics. So you're looking every 0.75 meters with this frequency range of 17.1 to 17.3 gigahertz. Depending on the antennas, which I'll point out in a minute, you can have a narrow beam of measurement, say 15 degrees plus or minus 15 degrees, or a wide beam up to 70 degree range of view. So with that approach, your strong reflector is what you'll see, and you need to know what's reflecting. That's why mounting the corner reflectors can be helpful. So what do? If you have at least a 10 to 1 horizontal to vertical slope or greater, you can resolve into the vertical component very precisely the displacement from your reflector. And it's just trigonometry to apply that. The advantage you can carry it out close to this without accessing the bridge or structure. You might have to mount the corner reflectors. You will have to mount them on concrete. There's very great accuracy. It's you're going to get the information that's in your antenna range, the view, and how powerful the reflector is provided. And it's up to 0.004. That's 4/10,000ths of an inch out to 1,000 meters statically. At 500 meters, you can go from closer in, you're at 100 hertz. Natural frequency responses can be measured. You can still measure 40 hertz out 500 meters. So on large, medium to long span bridges, particularly over water, this can be a real advantage for monitoring their performance. It can work in almost any kind of weather, and it'll take the data. So you're there, but it will take the data and record it. And it's on the order of seconds. It's very fast to take the data. So the first project we did was in conjunction with IDS and Dr. Bozharayanov, the New York City bridge maintenance engineer at that time. He was interested to go to the Manhattan Bridge. And this is the Brooklyn Bridge in the background. We set up on the Brooklyn side with a unit. There you can see one of the antennas. These are mechanical waveguides that can be changed. They'd earlier done a GPS study. Well, they did the study because it's a very large bridge. We set up over here. We shot out past midspan, line of sight, speed of light view that we could see. It's a very well-used bridge. It has 4 railroad tracks for the subway trains. It has 7 traffic lanes for trucks and cars. And it was because it was an old bridge and in suspension, as you saw, in severe weather and severe loading by the trains, it would twist up to 9 feet side to side over this 115-foot width. So they wanted to fix that. That was a lot of fatigue potential and movement for the bridge to take. So they took a torque tube system. It took them $900 million in 10 years to get rid of this deck torque of 9 feet in extreme wind and train loading, as I mentioned. But this really stiffened it. They first used GPS to check that by Columbia University, and it showed, okay, it's no longer twisting as much. At midspan, the 2 outer edges, it was twisting much less. It was still showing 300 millimeters of movements when train went by in this case. So we set up with our system, and we went right down the center. These great big steel girders every 5.5 meters were very good reflectors. We could even pick up, lining up carefully, the outside cantilever extension of those girders. So we checked for a twist between the center and the outside in a half day of testing. And these are the sampling frequency parameters. But basically, the crossing beams were very good reflectors. So we saw all those crossing beams. It's like a distance rangefinder because it is speed of light technology. You can see them going across. Here's a zoom in on what's the power of the reflectors. They stood out. So that was very easy to see those as well as the outside cantilevers. And the displacement time series, here's a half hour of data at mid-span showing 300, 330, 350 millimeters of displacement as trains went by. So this is showing the trains and picking off the center girder. This is an expanded view of that, 4 minutes of data, showing a train comes along, moves at 300 millimeters, the train goes on by, again looking at the mid-span crossbeam. So this is actually 55 crossbeams plotted on top of each other over a half-hour period because you're seeing, as long as you're more than 1.5 meters or greater apart, you get discrete measurements all the way across. So we were able to simultaneously measure all those beams very quickly. And when we plotted the results from this half-day survey of train traffic, the peak vertical deflections from the edge out at the cantilever to the center showed only 50 millimeters difference, and the maximum deflections that were measured peaked at 500 millimeters in the center and 550 millimeters on the edge. So a very good demonstration study that it was no longer twisting, that it was performing well. And we also did some background measurements looking at displacement time series of vehicle traffic with no trains. These are the trucks and wind. And from this data, you can get the natural frequencies of the system. And this is showing the results. This was related to slow plan transformation, but the real peaks are at 0.23, 0.3 hertz, and 0.49 hertz for this large bridge with expected low frequencies. So you can get vibration mode shapes and other resonant frequencies out of the IBIS-S data, which means imaging by interferometric survey for structures. We've also used it horizontally on buildings and wind turbines to look at horizontal motion. You got to pick 1 degree of motion, vertical or horizontal. And on bridges, it's vertical. This is that concrete bridge I mentioned earlier at the start. There you can see the IBIS system set up on it. These are the corner reflectors. Again, the corner reflectors on the top rail. We made up a system to stick them out in space. You can rotate them and point them at your IBIS unit. And they are epoxy mounted, but we sandbagged them just to make sure in case somehow the epoxy failed. It didn't. But these are very powerful. They do stand out. But without that, you aren't going to see a distinct reflector from the concrete. Steel reflects. Concrete doesn't. This shows a much smaller truck. It was around a little over 40,000 pounds. But when the truck went by, it did move it a few millimeters. And that was a post-tension segmental bridge that we'd actually done earlier testing on with impact echo scanning to find voided versus grouted ducts. And we did find some void in the duct grouting of the bridge. They knew they had some potential problems, so they addressed that. But this just shows that motion. And you can go to the natural frequency. Well, this is a blow-up view over a shorter time of the corner reflectors at the 5 different positions. And we only saw 2.26 millimeters peak to peak, basically tenth of an inch, that was observed in the middle of the mounted span during the testing trucks. So this shows the displacement spectrum, the frequency content, higher frequencies, smaller bridge, 1.3 to 3.55 hertz. The final one I'm going to show is a comparison of conventional load test results with IBIS-S displacement monitoring. This was an FHWA long-term bridge performance monitoring study with conventional load testing was done by Drexel University, and we did IBIS-S monitoring of this bridge in New Jersey, in the Wayne Township, northern New Jersey. And we monitored in particular one girder, 2W3, of the steel girder with a concrete deck. So here you can see nicely the focusing horn antennas. This wide angle means that it's a 15-degree view. And the small, opposite of what you might think, vertical dimension means it has a very wide view, more like 60 degrees vertically. So narrow view horizontally to focus on the antenna, the corner reflectors, and that's also good for testing stay cables, as we'll talk about in a minute. But it has a control PC, 12-volt power supply. The unit sits on a tripod, and you have a sending and receiving, and all you do is unscrew some screws to change the mechanical waveguide air horn antennas. So you can have different views vertically and horizontally, depending on what you need. This is back to that concrete bridge, just showing that again. But we put the corner reflectors up there. Why? Well, it only has steel diaphragms across, and it was a steel pan deck. So we thought that might be too much steel. It might be hard to get a distinct reflection. So we put corner reflectors on it. And so for this reason, they backed out 6 trucks, and they did them at like the quarter span, the mid span, and the 3/4 span. And so they were 460 kips of load. This is the Drexel string potentiometer down to the ground for precise measurements of displacements during the load testing. And we had our corner reflectors, not exactly the same spot, but as close as we could get them to where they had these displacement potentiometers. So you can see where the reflectors are now at these quarter span locations. And this is showing them in the plan. We wrote about this in International Bridge Concrete meeting in 2021 or 2022, I want to say. And also we first published in around 2010 or so at the TRB annual meeting for the earlier Manhattan Bridge I showed. So there are published papers. If you'd like to get those, just let us know. And the IBIS-S shows the ambient traffic that was going by on the bridge, and the natural frequencies again. It was a large peak, was at 2.76 hertz. This shows the end results of displacements for at corner reflector 1, 2, and 3, where 2 is in the midspan. Maximum loading was at the midspan. It moved over 0.8 of an inch. And you can see how this was done over time and as the trucks were moved and monitored all these locations. So when it was compared between the potentiometer, the maximum displacements versus the IBIS, it was very close. And that's what they've shown in research by IDS GeoRadar, that it's very precise, compares very well with physical measurements. So it can also be used for state forces, tension forces, and state cables. Accelerometers are traditionally used, you have to mount them. And they have to be mounted. Doppler laser can be used, but you only get one state cable at a time. And it's not as precise. So it gives you, with the IBIS-S, you can monitor multiple cables. You get static and dynamic displacement measurements, very accurate, much more accurate than the laser displacement unit. And No traffic shutdown is needed. You do have to have a stable point to mount it, the IBUS base unit to take the data, and it is line of sight speed of light. You have to see what you're measuring. So you line it up so you don't hide cables. And by doing that, as long as the cables are more than 1.5 meters apart, at your focus point with a narrow beam antenna, you get very good results. So Carmela Gentile, Guido knows personally, was involved in this study, wrote about it first, and it's showing some of his work here where he set it up in displacement versus time vibration data. There's the antenna looking up at it, and the stay cables, because they're steel, stand out very well in the sky, that you know where they're coming from. And it compared with accelerometers, they're virtually the same. This is integrated displacement results of IBUS S to be acceleration. Compared it with the accelerometers that are mounted on this, Wilcoxon Research accelerometers, it worked very well. The IBUS actually had more resonant frequency peaks, and then weren't quite as clear in the accelerometer response. And tension forces calculated from the equation of the unit weight of the cable, its length, etc., natural frequencies, compared very well between the accelerometer and the IBUS unit. So we've done some work on our own on this, and here we're looking at 8 cables at night on a large stay cable bridge. And they also had a mounted accelerometer for comparison's sake. This just shows some of the results of these various cables where you're getting excited by traffic and wind. Normally that's enough to excite it. This is a single cable result of displacement over time. Then you analyze this, you go to the frequency domain, and you get the natural frequencies. So this is showing those natural frequencies of the 6 cables in this case. And of course, the longer cables had lower resonant frequencies as expected. And this shows a single cable again where the accelerometer is mounted, 2.7 hertz, 5, and 7.2 hertz natural frequencies. That compared very well to the accelerometer response, 2.71, 5.2, and 7.3. We predicted the forces and came up with a stress of 128 KSI versus 118 design stress. So it's a very good economical system to get a lot of data quickly in the field for stay cable forces. And to summarize, it's very accurate. You can measure bridge load test to 4/10,000ths of an inch, 100th of a millimeter, with corner reflectors needed on concrete bridges, maybe not on a steel bridge. You still might, though. Get natural frequency measurements from 0 to 100 hertz. Vibration monitoring predicts stay cable forces from ambient vibrations, or you can impact them if needed. We didn't. And excellent correlation was found between the IBUS S and the accelerometers. We've used it on dynamic horizontal displacement monitoring of wind turbines and buildings. And it is line of sight, speed of light technology. Your reflectors have to be visible and clearly identified as to distance in your data, so you line up to see the reflectors and the cables. So I think that's just a repeat of much of what I just said. And there's my contact information. We will post all this within a week or less up on our website, so you can go back and see this. And we have both the Colorado office and our Maryland branch office. So I want to introduce now Professor Guido Camata. He's the technical director of ASDIA in Italy and ASDIA USA in Denver, Colorado, specifically Golden Incorporated. And Olson Engineering and ASDIA we're jointly pursuing projects to provide clients advanced NDE monitoring and modeling services for bridges, buildings, and other structures. As I think you'll see, our own work at imaging the infrastructure and testing it very much complement his work that he'll tell you about for modeling and everything else. So with that, I'm going to close my talk and change the share and start again his talk and let Guido begin. Okay. Guido, I will give you the controls.
Thank you.
Thank you very much.
Thank you. Thank you, Larry. And good morning, everybody. So, like Larry said, I'm Guido Camata, the technical director of the company. And I'm also a professor. Like, I actually graduated my PhD from Boulder, here in Colorado. And after then, I did a lot of research, mainly in finite elements, linear modeling, and also structural health monitoring. So I started the company in 2009, and since then we grew in time. And I'm going to also give you
that one.
yeah. Today, I'm going to talk about numerical simulation and also digital twinning and artificial intelligence using sensors. Just a brief description of who we are. We are actually part of a holding. The holding has a turnover this year, probably around $35 million, more or less, is in euros, but is increasing. We are more or less 200 people. And we are part of this ecosystem in which our company, as they works in structured monitoring of structures and infrastructures and finite element modeling. And Hydro Studio, that is our partner, does the same in the with hydraulic systems. So they use artificial intelligence for leakage of water and other design and other opportunities in the hydraulic sector. We started, actually, we have more than 160 publications now, so it's an older. We started as an engineering firm, and we developed from the beginning very advanced solution for very complex structures. Like in this case, is the largest telescope in the world. We're in charge of the 3D seismic isolation system and also the seismic amplification. Since we are developing this type of projects, we also started a software company around in 2012, 2013, started developing software for other companies and also for the market, mainly in advanced simulations, artificial intelligence. And in 2020, more or less, we started a hardware company because we realized that some type of sensor were missing in the market, especially low budget sensors for like infrastructural monitoring. We are more or less everywhere because our software is sold in several countries. So the name is SDKO, but we also do a lot of consultancy in a lot of different countries. So what we do, as I told you, we develop software for external companies. This is one of our like business. And our software is used, as I said, by several thousand of engineers because some software like the one of Caracol is used a lot around the world. Our main software is this one. It's called SDKO. It's based on OpenSeas, an open source from Berkeley, but we develop on the top of this open source several other constitutive modeling and other more advanced simulations. We can model with no linearity very sophisticated projects using, we model every single rebar and we model cracking, creep, shrinkage, and all the other features for the concrete. So we are able to detect cracks and do very like really advanced simulation. So for structural monitoring, already Larry mentioned, I just wanted to add a few things. So basically, structural monitoring system provide continuous measurement means that we measure the behavior of the infrastructure or structure 24 hours per day. And I'm going to show you how. We use several types of sensors. So accelerometer, displacement, drift sensors, strain gauges, fiber optic system, tilt inclinometers, and also obviously temperature and environmental sensors. We also use cameras and several different type of measurements. So the idea, and I'm going to show you, is how we can observe the behavior of the bridge or the structure, detect if something is changing. I'm going to explain you what I mean with that, and try to predict early signs of damage or deterioration. So there are two approaches that we use, and it's very important to understand how it's used. The first one is called data-driven, that is mainly based on artificial intelligence. And how we do that, we measure, as I told you, 24 hours per day, the sensors, and we use the sensor to do our measurements. So first of all, we use a pattern recognition of the data. So we have the data 24 hours per day. We try to detect to reconstruct the signal using several different features. And then when we know like all the signals, we are able to predict if something is changing. So it means basically that the artificial intelligence is learning from the sensors and produces statistical indicators and anomalies. So it means that if when we reconstruct the history basically of the acceleration, for example, if you see a deviation in the acceleration and in terms of several different features, this is an anomaly and could be an instant anomaly or a persistent anomaly. In the case of persistency, we give indication to the clients and pay attention because, for example, we notice that acceleration in terms of a certain signal is changing. So we need to investigate more deeper. So basically, the artificial intelligence is learning in time, learning what's the behavior of the bridge, and can detect if there is something that is changing in time. That's very important to see the performance of the bridge during the operation or during the normal environmental condition. So because right away we can understand if, for example, a support is changing this behavior or the joint is changing somehow. And so we are able to detect early, basically anomalies. But this, with the data-driven, that's very important. It's impossible to evaluate the safety of the bridge because the demand is completely detached from the capacity. So if you want to evaluate the safety of the bridge, it would be very important also to have a model-driven, so to have basically finite element model. And this finite element model obviously is based on structural mechanics and use a physics model. So we know the capacity of the bridge. And how we produce this model, and it's very interesting. We use the sensors to calibrate the bridge behavior. So we know that with the sensor, we know the frequency. I will show you later. We know the eigenmodes, so we know the stiffness, the mass. What we do, we calibrate the model initially manually and then using Bayesian updating, so it's continuously calibrated. And with this model, we can do a lot of like calculations and we can have a lot of information. So just to give you an idea, we use first the data-driven approach to have a faster response. Then if we get an anomaly, if we get something that we think is important, we use a model-driven to study what is happening to the bridge. But I will show you later, it's also very important for not only for safety assessment, but also for decision making. So it means that we use the model, for example, to predict scenarios in the future. If there is an earthquake, there is a flood, or if there is a certain deterioration, we can predict in advance what happens to the bridge and how we can intervene. That's very important for maintenance because the problem of bridges is also maintenance, also in time. So just an idea of this, we need to pay attention about the inflation with the artificial intelligence, because as I told you, artificial intelligence can learn only from data that are available. So can learn only from data that are in operation. So from traffic, environmental data. I hear several times that you can give you indication on safety. No, can give you indication only on performance during like the operation. That's a very important, obviously, information, but it's nothing related to safety. So if you want to go into safety, it's very important to understand that you need even a simplified calculation, hand calculation, or a finite element model, or what is something that is related with the physics. So what we do, we combine the two things. As I told you, in operation, we use artificial intelligence, but for extreme loading, for ultimate capacity, for other information that are related to safety, we always use also calculations. So the key message has to be always this. Data-driven can tell you if there is something unusual that is happening. So something is changing. The model-driven instead can tell you if you are safe and how much you are safe, what the ratio between the demand and capacity. It's very important because I told you like there is a lot of confusion in the market. And it's very important to understand if someone comes to you and tells you, oh, I use artificial intelligence to study the safety, is totally wrong. So this our system is composed by several different sensors. I told you like we have a sensor for acceleration, dynamic sensor for acceleration, inclination, velocity. all combined with the thermometers. They are connected with Ethernet cables, so they are very cheap cables, and go to an Ethernet switch and then to an acquisition unit that is a normal computer. The computer, what it does, synchronize all the sensors together. It's very important to evaluate the frequency and the eigenmode of the structure. They have to be always synchronized. And the synchronization can be done on thousands of channels, which is what we did. And then we have also our acquisition system that we can use to read the potentiometers, strain gauges, anemometers, every type of analogic sensors. And everything goes to the same computer, and we can basically collect all the information that at the end go online to a platform. So in the platform online, you can read all the information regarding the functionality of the sensors, so if they are working, how they are working. You can read all the data in terms of statistics, artificial intelligence, digital twinning that I will show you later, and then also all the functionality of the dashboard. So first of all, just a few information. What we can do also with our sensors is to evaluate the frequency and the stiffness, and so eigenmodes, mass, during the construction of the bridge or during the construction of the building. We are using it now in some construction. So why this is important? Because when you are designing something, you never know if what you design is actually implemented in real life. So if during the design you are able to evaluate the stiffness and the mass, you can even change the finite element model to be sure that everything is calibrated. That's very new compared to what is used normally, because what normally we do, we use conventional models. In this case, what is very interesting that we are using real model connected to the structure. So this is an example of one big hospital that we are designing, what we are proposing. This is roughly a 400 million euros hospital. We designed the seismic isolation. In this case, we propose the client to use our sensors during construction, as I told you, to calibrate what is the damping of the isolation, to calibrate the stiffness, mass. This gives us a lot of reliability and confidence on the model. And when you have certain type of structures, it becomes very important also to have more information regarding the structure and more and be confident on what we are doing. And obviously, we leave the sensors at the end to evaluate the performance of the hospital, because the hospital needs to be ready just after an earthquake. This is what we do in structure when I was telling you about artificial intelligence. So we use the sensors. We read the signal of the sensors, and here you can see upright the statistical data of the inclination. So we can see obviously the inclination due to temperature, the environmental condition, traffic. You can see basically the difference day by day. And with artificial intelligence, we do exactly this. So we detect what is a healthy pattern of the bridge. And then if something changes among like several features on the bridge, we provide the anomaly. So if the anomaly is just instantaneous, it's just an information, but the anomaly keeps on being persistent, we give the information to the client and we need to do investigation. So just to give you an idea, if the inclination, for example, of a pier is changes just instantaneously, so for a fraction of a second is outside, is anomalous. For us, it's normal behavior. It's just, a normal anomaly. But if the inclination changes in time and there is a persistency, we give the information to the client and we start investigating the problem. So the big advantage is, in this case, we can monitor the performance of the bridge, and if it's changing, we can give a projection to this change and tell the client, for example, pay attention, you need to change the supports in 5 years because we see that the behavior is changing. So from this, as I told you, we need to extend this information to a numerical model. That's very important because we need to go, if we want to evaluate the safety of the bridge, we want to evaluate the performance of the bridge and evaluate also the capacity. Is very important to connect this artificial intelligence information with our basically physical model. And so we develop digital twins, not for every bridge, typically for bridges that are more important, but we have our real, you see real data that comes from the bridge. So from the real data, we get basically the information regarding the frequency, I told you, stiffness, mass, damping. We build our numerical model that is a digital. The digital is always synchronized with the real. So it means that we have a real model. That's very exciting for an engineer because for the first time, I have a model that really represents the reality. It's never like that. Being a researcher, I know that it's impossible to have a model that represents the reality. And with this, we can do a lot of things because, for example, we can run stochastic traffic. So the stochastic traffic in time can help us to determine, for example, if there are fatigue problems, like in this case of this bridge, the problem was fatigue, or we can see the state of stress. We can even run extreme situation like seismic response. So increasing the acceleration at the base of the bridge, we can evaluate the demand versus the capacity and see a damage scenario. And we can even train the artificial intelligence with this. And basically, if we are able to do that, after a few seconds of an earthquake, we are able to tell you exactly what are the components that are damaged, if there are damaged components, just using artificial intelligence, because we use the model to train the artificial intelligence. This is the idea of an hybrid digital twin, where you use artificial intelligence and digital twins to obviously give information resilience about resilience of a certain infrastructure or even a network of infrastructures. I'm going to give you some examples of digital twinning. Another bridge, there's a post-tension, pre-tension bridge actually, where you have, you see the operational model analysis with all the sensors, like what Larry was showing. And we build, as I told you, the digital twin based on this information. So we have always a digital twin that is synchronized. Just an idea of how the model is made is a nonlinear model with fiber elements, with the cables. And you can see the modes synchronized basically on the bridge. And as I told you, they are synchronized in time and with automatic synchronization. So you can see the difference between our operational model analysis that we do with our software and the digital twin. And as I told you, like we make sure that everything is always synchronized. And for the synchronization, obviously, we use also environmental data because the frequency changes because of temperature, humidity. So we always have to consider the fact that the environmental effects are typically on the frequency more important than the damage. That's also a very important thing because another thing that a lot of people say that they use frequency to detect damage and is totally wrong. If there is a small change in frequency, it means that probably the bridge is so damaged or is even collapsed. So the frequency, the damage is not absolutely, frequency is not a good indicator of damage. We need to use other indicators. And this is an example of a digital twin that I really like for a bridge that is actually a railway bridge for an airport connection. And as you can see the wind, and then you can see when there is the train, how the deflection is changing. So if you think we can run 20,000 basically simulation of the train and tell you what is the prediction in terms of fatigue, so life prediction, or in this case we are more concentrating on the support and the connection between the supports, and we are able to detect when one support is breaking way in advance and tell the client to basically do the maintenance before they need to stop the bridge or interrupt the bridge. This is another example we use a lot also for historical buildings. We had the data for this building for 22 years. It's a very old tower, inclined, was built in the 12th or 13th century. And you can see upper left, sorry, there are the cycles of inclination due to the temperature, humidity. And also we try to correlate it with the water level, so the water table. And then we try to get information using artificial intelligence from this data. I will show you the results. And then we decided also to build a digital twin, synchronizing the tower with our numerical model. Also, this is very interesting because you can use, for example, 22 years of data to run the finite element model and see what is the level of damage that the tower is sustaining due to this cycling. And these are the results that we are obtaining. And it's very important to look at this because also the most important thing is not really the data, but the data, the interpretation of the data. So we showed the client that in 2013, the tower started giving some anomalies in terms of inclination, and the anomalies are increasing in time. And also we use statistical data to give the same information. That's a very important information for the client. And the first information, something is changing. Artificial intelligence is telling you this. Then the digital twin is telling you what is the level of basically inclination that is acceptable for the tower before being like a risk. So you see the transition between the artificial intelligence and the information that basically the model can provide you. We did other studies also. This is a very interesting bridge in England. We did it with the University of Bristol, our partner. And Clifton Bridge is 160 years old. It's one of the most important bridges for sure historically in the UK. And we did the studies with Professor Derisi. And he was studying also with our finite element model the behavior of the bridge. And these are the basically frequency that he identified. And we are studying also the behavior of the bridge. And the idea is to build also a digital twin. We are running, like now we are evaluating more than 100 spans. So we have a lot of data and also 30 buildings. And we have several also digital twin already completed. So we have a lot of information and experience. We also combine our effort with Kistler, is a Swiss company that produces as well sensors, but they also produce weight in motion technology. It's very interesting. They're able to measure the weight of the trucks divided by axle and when the trucks is moving. So what we do, we interface with their weight in motion. We read the data from them, and we can run in automatic, basically the finite element model, and see what is the deflection or what is inclination or stress on the bridge. That's very important for load rating, for example. So if you have a truck that is exceeding the design load of the code, then we can basically test every time the bridge for loads that are exceeding the expected load from the code. We also develop software, for example, for load rating. So we are able to, in this case, we show is a highway. So our client was a big highway in Italy. So we developed this software to let them do all the calculation in automatic for bridges that, for trucks that exceed the design loads for the codes. So they can click on one entrance to the end, intercept all the bridges, and they can do the calculation in 1 hour, for example, 100 bridges, and see if the truck is damaging the bridge or it could cause problems. In Italy, we have a huge problem for like trucks that are way beyond what is the codes. So we need to evaluate every time if we have a problem with a bridge that basically is in the way of the truck. We also, with the digital twin and with artificial intelligence, provide information of early warning. So basically, it's very important to understand that the digital twin has to be alive. So we get information from the sensors, but we transfer information to the client or to whatever we need to tell them, pay attention, there is an anomaly that is persistence. We need to close the bridge or we need to evaluate the bridge. So we provide information in real time to be sure that the client is running safe. And this is the dashboard that I told you, like, so basically it gives you all the information I told you online regarding statistical data, artificial intelligence, the digital twinning or real-time data coming from the infrastructure. So in terms of deflection, inclination, acceleration. So also the client can see in real-time statistics, but also the real-time. Just 5 minutes and I'm going to show you the last two things. So maybe we can have also a few minutes to discuss. So our finite element program, as I told you, is very advanced. It's developed to evaluate the capacity, especially assess the capacity of existing structure, so bridges and buildings. We work a lot around the world to show what is the performance of this type of simulations. And that's very important because right now we have a lot of issues, as you know, with existing structure, existing buildings. existing bridges that are at the end of their life. So we need to evaluate the capacity of this building compared to the demand. And if we use simplified calculations that we will have always to use to see, a first approach, but we will have to close a lot of bridges, or we will have to strengthen a lot of these bridges and the infrastructure and also buildings. This is our experience. But in reality, these structures, for certain reasons, are still safe because the real behavior is way more complicated than what is a stratified model or a simplified model can describe. So what we do typically, we help engineers to try to understand the real behavior of the bridge and to give the real performance of the bridge. That's a very important, I think, solution. And our program can take also consideration non-linearity of the material, but also non-linearity of the geometry, so large displacements. We do a lot of evaluation of bridges, as I told you, also for seismic performance. In this case, we can see the fiber strain, so the stresses in the steel. We do a lot of soil structure interaction. We believe is very important. And actually, we already started working on that also in the US. This is the Osman Ghazi Bridge. We wanted to evaluate the performance of the bridge under seismic performance, but for considering the soil structure interaction. It's a very large model, but we build the model step by step, also considering also the construction stages of the bridge. Next one, yeah. This is actually consultants we did in the US for the performance of shear walls. As you can see, the red and the black. The red is the experimental. Our black is the results. It's very good in cyclic. And you can see we can model steel yielding, cracking, crashing of the concrete. And this model that until 2 years ago would have taken like probably 2 days to run, with our model, because we develop a very sophisticated implicit solution, it can run probably this one in 30 minutes or less with the entire cyclic behavior. We do a lot of work with punching shear, also of transfer floors, flexural failures, because as I told you, in this case, there are a lot of different effects that like the linear elastic analysis don't take in consideration. So for example, for slabs, for bridges, what happens when the slabs start cracking? It expands laterally. That's a very well-known behavior. So the girders basically restrain this expansion, increase the axial load within the membrane, and increase the capacity. This is a real behavior. But if you run a normal linear elastic behavior, you would never be able to exploit this additional strength that is a real strength of the bridge. Just to show you this example, we run 100 of these models per year. So that's the first bridge that was made in Europe, made of glass fiber reinforced polymers rebars. So it's very interesting concept because we decided to use a pretension. You see the gray cables, they are inside the beam, and they have a concrete cover of 13 centimeters. But for all the external rebars, we use glass fiber. So this increases a lot the durability of the bridge, obviously. And we tested the beam, real beam, 26 meters. And we also did all the prediction with our models and also the setup. It's becoming more and more interesting, the glass fibers, because now the ACI have their own guidelines, so they were approved. You have the certification. In Europe, we have our certification and our codes. And even Saudi Arabia now, they have a code that was approved for the glass fiber. So in the future, they are going to become more and more interesting because of durability and performance. We work a lot also with Mesory, but I guess like, let's keep this part. We model entire buildings like brick by brick. And with very sophisticated also impact elements to study the behavior. As I told you, we have a lot of experience around the world also for seismic amplification, soil structure interaction. Actually, it's a very interesting project. It's called the Cherenkov Telescope Array. It's the largest array of telescopes in the world in Chile. There are more than 100 telescopes, and we are in charge of the basically definition of the seismic activity on site. So seismic amplification, the spectrum, and also we have to give them the oscillograms to use for the nonlinear time history analysis. And the same we did for the ELT telescope. We were in charge of the soil structure interaction and also the amplification, seismic amplification. So you can see we do a lot of this type of analysis for evaluation of especially existing performance of bridges or buildings. Just the last thing, so we do, as I told you, we do a lot of projects with monitoring system for structure and infrastructure. We work a lot with sensors, so we sell sensors. We work a lot with nonlinear complex analysis, and we do also design around the world. And our software, I told you, is called SDKO and is sold more than 100 countries and is very popular among university institutions, but now also this nuclear sector, bridge designers are starting using it because they realize that they can have a lot of advantage. And so thank you to Larry. I'm very happy about this collaboration. So
Yeah, thank you very much, Guido. I'm also very excited about the collaboration. I think it's when we first met, I met his wife who was working with the World Trade Center locally, and she said, "You should meet my engineering husband. You guys might have something in common." So we got together and started talking in February when he came back, and it has led to our pursuing a strategic marketing alliance and offering both our U.S. presence and as he grows here, but also supporting in the field. And then he can very much handle the monitoring and the sophisticated modeling. So, and it's exciting to me because I think one thing that we will add to our capabilities for load testing of bridges is with his capabilities to load rate the bridge. And ties into the IBIS system for active load rating. And it doesn't have to be long-term monitoring in that case.
yes,
That's more of the active testing, with the distinction that when we go towards the structural monitoring long-term, it will be very much using the ASDIA sensors and the integrated system that they have and the digital twinning. So I'm going to open it up to questions. Anybody wants to sing out a question, unmute yourself, and we'd both be happy to answer them about our respective talks. But thank you also in general for attending, but we're not closing it just yet. So does anybody have a question?
we can stop share if they want to.
I'll stop the share. Okay. Maybe we gave you too much.
Yeah.
I'll throw out a question.
Larry, this is Russell Batman. I've got about 10 questions, but they're best handled by a sidebar. But for now, though, I'm wondering if you might delve into what might be involved in testing the the lateral movement of large ships' piers during the berthing and mooring of large ships. The berthing action is when the ship makes first contact with the pier, and then the mooring is during a storm when the ship is pulling on the pier with its mooring lines. You mentioned that different of the monitoring techniques would only handle one axis. Basically a pier is a bridge to nowhere with a lot of lateral capacity. So might you spend just a little bit of time discussing the application for large port harbors?
I'll start on this and let Guido continue. We had one project down in Honduras where they had a more flexible than desired pier where the cruise ships were coming in to dock. And so we did use the IBIS system to monitor displacements. And so we learned a few lessons out of that. One of them is to be careful so that as the very large metal ship approaches, it can obscure some things. So you have to be careful how you're monitoring it so you don't see the ship so much, which is a challenge. But we did get useful data. And what that means is that you have to line it up in such a way that you can minimize the effects of the ship coming in.
Yeah, like we have also experience. We are working in Dubai now in a port, and we are trying to expand also this sector. Actually, there is a very interesting project that we are trying to get like now. Is you can also combine what is very important is to fuse different type of sensors. So in this case, You can have inclinometers that are actually 2D inclinometers, so you can measure the two different directions. And you can combine it with cameras, for example, for the displacement, and with accelerometers. With all these, you can have all the information regarding frequency of the pier, how the pier is moving, and what is basically the damping during the impact or during the movement of the ship. So you can definitely have a lot of information regarding the behavior of this type of structures. And it's becoming more and more common, I have to say, because a lot of ports are interested in this type of evaluation of the performance. Because
Yeah, and Russell, remind me who you're with. I forget.
Naval facilities.
Oh, sure, that Russell. Thank you.
there is another question in the chat, like regarding that's not where the question. So maybe what's the first one? Okay, this one.
That was early. There's 3 new ones.
Okay.
Try and click.
Yes, but if you make it larger, so
Let's see. Thanks for Amara's compliment about presenting. Let's see.
yeah.
We don't design and build our own radar boards. Other groups have done that. The IDS GeoRadar is from them that we used in the IBIS system.
Then the next one, what?
Then you want to know the approach. This is probably for Guido
Yeah.
for checking real-time monitoring data.
Yes. So the question is, what is your approach for the frequency of checking real-time monitor data? Do you set a threshold warning based on IE and what's the schedule basically? So it's complex in the sense that we have different thresholds. So as I said, like it's real-time, 24 hours per day. So the first is called the anomaly KPI that we are measuring is what is an instant anomaly. And in this case, we just provide information to the client, telling the client the signal is anomalous, but there is no problem. If there is a persistence in the signal, so if persistence in time and also intensity, then in this case, we give a warning to the client, or even a critical warning, telling him like, pay attention, we need to intervene, either like we need to investigate, or even we need to close down the page because the persistence and the anomaly is too high. So this is the approach that we do. And it's never based only on so the frequency is basically continuous, is what I'm saying. Like we measure the acceleration actually 1 kilohertz. So
continuous real-time monitoring is the standard for structural. It allows you to trigger.
Yep.
And then Aman Hosseini asks in the chat, yeah, the IBIS system I showed for the Manhattan Bridge. That is an old suspension bridge with the steel frame and cross beams in the girders in the deck area. And it was about, we were at midspan around, I want to say, 250 meters, I think, was midspan. So the total span was over 500 meters. We saw out to about 350 meters before we were constrained by line of sight from actually being down on the bank. And we just couldn't see beyond that. So it is speed of light, line of sight in the IBIS system. And so that's basically it. The maximum deflection we measured was 500. We saw 300 to 350 millimeters in the particular result I showed you at midspan. Okay. Thanks for your question. There was a fascinating study.
I have a question.
Yes, go ahead.
For the GPR, is there a possibility of seeing beyond a certain depth, or GPR itself is just, I'm talking in terms of piers and drill shafts, like can we, for existing foundations, which are like 3 to 4 feet, and we don't know the depth of those foundations, is there a way that GPR can be used to identify the rebar size, the spacing, and then what depth does it go, or what do you suggest?
Well, we do a fair amount of GPR in our normal work, and the ground penetrating radar, if you have of course, you need access to the top of the, say, footing in the first place. If you have to go through soil to get to it, you're going to have a hard time seeing the bottom of it. Sometimes you can, through soil, see the top and bottom of a footing, but it's not always so easy. And the steel also can act as what they call a Faraday shield. If there's too much steel in it, you won't necessarily see the bottom. But if you can get to access to top, seeing with radar, you can go fairly deep with radar, but then the steel comes into play. So we typically have seen tops and bottoms in one of our other case histories, like 3 to 4 feet deep without too much trouble. If it's just thickness of the footing, we would use impact echo and surface waves or sonic echo approaches to go up to 10 feet or more and get the thickness of, say, a more massive footing. So it all depends, but you do need to get to the concrete is always better. And you go to lower frequencies in radar. Most structural radar is between, say, 1.5 to 3 gigahertz. And that will penetrate to maybe approaching 3 feet, depending on the system. And lower frequencies will see deeper. Like when you're doing some of the utility work, you're typically working with one system we have is a impulse radar pinpointer that goes 400 and 800 megahertz dual antennas. And depending on whether it's sand versus clays are very limited. You might see down 10 to 15 feet. Then you go to really low frequencies, we've seen down as far as 75 feet in soil cases, soil and rock, with a 300 megahertz impulse radar crossover antenna we use. So it all depends. But if you have something in particular, just send us an email. Happy to address your particular situation.
Yeah, thank you. Thank you so much for the presentation. It was really informative.
Sure. And we will be posting this on our website. We have a number of other presentations up there as well. And both Guido and I are happy to answer questions from people that want to reach out to us.
Sure,
And
absolutely.
Because of the time change, if you're in America, but he works around the clock, I hear.
Yeah, exactly.
But he's in America 2 or 3 weeks, approximately, a couple weeks, approximately every month and a half, something like that. So he's often coming to Denver. Okay. Any other questions?
Larry, maybe you covered this, but I wonder how you control, for survey control horizontally and vertically. How do you have somebody set that up initially, or are you using GPS? Again, if you cover that
in the IBIS system or the deck scanning?
Well, either. I mean, how are you?
Okay.
How are you basing your survey control? The assurance that the horizontal and the vertical starting point, right, are accurate.
Yeah, I mean the GPS we do when we need to. We set up a base station as well as a rover that's a deck scanning unit, and that gets us within a few centimeters.
Okay.
Interestingly enough, some of the states, Indiana, Minnesota, and there are others, have a statewide network, and you tie into that without having a base station. You can also get within a few centimeters with the modern. We happen to use the emlets. There's a variety of GPS units out there. Trimble has them, etc. But we happen to use the emlet.
Okay.
And you will get within 5 centimeters location. It's amazingly accurate.
VRS.
Yes, GPS.
Okay.
But the other one is the IBIS system is sort of a rangefinder to begin with. So as long as you know where you're based at, and that's important, but it's a distance finder. We have taken along a simple distance finder to point at things to verify that indeed the reflector we think it is that beam, say. So we're confident of where our reflectors are coming from. The Large Manhattan Bridge was really good because it was so deep, 5-foot deep beams, and regularly spaced every 5.5 meters. They stood out in the data. But then that other steel bridge I showed, much smaller with all the steel panning, we needed the corner reflectors, and we located where they were because we thought there was too much steel. We wouldn't know what it was reflecting from. So the corner reflector was kind of a focusing mechanism. And of course, you need that on the concrete bridges.
Okay.
Okay.
Thank you. A lot of it's over my head, but really interesting.
If you understand the applications, that's our first goal. We have the papers to back it up. Anybody that wants a paper, some of them are on our website, or just email us. And Guido also has many papers. We'd be happy to share them with you.
Sounds good. Thank you guys for your time.
Oh, thank you. Appreciate it. Appreciate everybody's interest. I know a number of you I've met personally. I forgot, Russell, I didn't recognize your last name. But maybe I never saw it, always just Russell. In any case, a number of the other we've met, like I say, if you ever are in our area, feel free to visit it. And you'll continue to, I think, see us together pursuing these structural monitoring projects where we feel it can be a real benefit to people over the short and long term. And the really sophisticated monitoring, I think Guido could speak to this. It tends to be larger, more important bridges, or they have critical monitoring needs because they're worried about it.
Correct. Absolutely. Like if you have deficiency in bridges or old bridges, it's a very important like solution. Or for new bridges or new buildings that are critical also.
One thing he didn't mention so much is he's actually been able to monitor the effects of corrosion of rebar.
Yes.
Not just and cracking propagation. And because they're so good at going, I don't know if people picked up on this, from linear to nonlinear because of all their earthquake loading, that still is very important as you get into failure mechanisms to be able to go from linear to nonlinear. You can speak to that better than I can. I just bring it up if you want to comment on that.
Absolutely. Like from our experience, like we work, I told you, like in several places. We have been working lately in the UK, and we showed the client that they can basically save a lot of money because a lot of items that are not verified with linear elastic analysis, we can show them why instead they are perfectly safe using more advanced solutions. So we always compare the linear elastic, like we always compare the hand calculation, but then we prove why a certain condition is safe. And when you have big buildings, a lot of money that you can save, or bridges that you don't need to close.
Yeah, and I think one other thing that there was a lot in this presentation. If you have your structural design drawings, they can pretty much import those into the modeling efficiently.
Yeah, absolutely. Yeah, it's a very efficient system, like for sure. Like now we can prove that is also economical efficient to make the evaluation.
So it probably won't be a routine small bridge that it's normally done on, but it can be.
You can. I mean, the cost of strengthening is always way more important than the cost of the analysis. And in addition, the big difference I always try to explain is the fact that we can show exactly, or with a good term of approximation, what the safety of the bridge is not a conventional calculation. So
yeah, and where you have on some of our bridges, of course, there are wave motion sensors, and they're often Kistler, and they're integrated directly into that type of data.
Yep.
So that can feed into the whole system.
Yes, we have very good collaboration with them.
Okay. So